Hello, it's my pleasure today to talk to you about the upcoming release of MSC Nastran 2013. This release is the culmination of the work that's been done in the last year since the MSC Nastran 2012.2 release. The first question that everybody asks is, when is it going to be released? So the answer to that is it's going to be released in the next few days on Windows 32, Windows 64, and Linux 64 platforms. So to do the quick summary, what we have is with each release we try to attack a few different themes to help our customers and our users out. And the themes are improving the performance of the product, improving the ease of use of the product, focusing on composites and durability. This is both for the aerospace industry and the automotive industry. Improving the nonlinear capabilities in both SOL 400 and SOL 700, and addressing particular needs for industry segments, and this is again mostly addressing the automotive industry and the aerospace industry. So I'm going to kick things off and talk about something we're calling MSC Nastran Embedded Fatigue. And the motivation for this is that many of our users basically have asked us to improve the capability so that they can determine what is the life prediction of their part or their life prediction of their assembly. And because material damage, material fatigue is very important to engineering solution, they wanted to perform simulations that do not require as much prototyping or as much experimental work as using existing methods. So what we have done is we've put the technology that exists in MSC Fatigue, which is based upon Patran, directly into Nastran. What the technology that's in Nastran today in this release is complementary to the technology that we have in the Patran product. So what does this capability provide you, the user, is it really provides faster solutions. It provides ease of use in having a single tool to utilize stress, number of cycles, N diagrams, or strain N diagrams. And finally, it allows you to optimize your designs based upon fatigue information. So what we want to do is we want to go from the design world to the analysis world to the life prediction in one easy step. In the Nastran 2013 release, this is available for SOL 101, SOL 103, SOL 112, and SOL 200. As I mentioned, it can utilize material data for either stress life, SN, or strain life, crack initiation, to determine what is the life and what is the safety of factor based upon your current design. It is very well documented, besides, of course, the QRG and the release guide, but there is a completely new manual that discusses the use of MSC Nastran Embedded Fatigue. And we will have follow-on seminars that also talk about the details of fatigue analysis. What the user does when he runs a Nastran SOL 101, a linear analysis job, one can have multiple load cases and obtain the stresses of those load cases or the strains, and combine that with tables that indicate the time history of that particular load. For example, whether or not it's a sawtooth history or a sinusoidal history. And the combination of those two things can be combined into duty cycles, and then we'll do a rainfall analysis to count the number of cycles, combine that with the material data, and use that to predict the fatigue life. A similar process occurs when one is in a SOL 103 or a 112 process, where now we're going to do a modal extraction, do a stress recover of the modal stresses, and proceed to do the same type of process to determine what is the fatigue life of your model. Here's an example of a problem, came out of the automotive industry, and really kind of highlights the gains that this new process can do. In the old process, somebody used Nastran, and they used some competitive fatigue analyzer. They didn't use MSC fatigue. And to do the simulation only took 11 minutes, but to do the fatigue post-processing took 8 hours. In the new process, based upon our customer using this in the beta release of Nastran, it took only 38 minutes, so 12 times faster in doing the analysis. And the key words is it's taking the technology and no longer looking at fatigue as a post-processing operation, but building the fatigue right into the simulation aspects. Another wonderful capability is that because we have the fatigue modeler built into MSC Nastran, we can utilize it for optimization as well. So we can say that we want to optimize a part to satisfy the constraint that a certain number of cycles are achievable. Or we can say minimize the mass, but at the same time the objective function is to maximize the number of cycles. So here's a simple example of a beam with these cutouts and optimizing the shape. And if you would have not included fatigue in your simulation, you would have gotten a great reduction in the mass, but unfortunately, after you took that design, you would have performed the fatigue analysis, and you would have determined that the number of cycles was only 100,000. But if you combine fatigue as a constraint in the optimization process, well, unfortunately, you don't necessarily save the same amount of mass, but you keep the durability to be very high, 100 million cycles, so that effectively reduces warranty costs and makes sure that your customers are happier as well. This capability can be used or can be accelerated by using parallel processing. So it will use the DMP license, and it will scale very nicely based upon the number of threads that you have in your machine hardware configuration. And that's set on something called FTG PARM. But there are a series of input cards required to define the material properties and to define the duty cycle if there's a combination of loads before one can perform a fatigue analysis in MSC Nastran. The next topic that I want to talk about is poroelastic modeling. Poroelastic modeling is for improving your acoustic analysis, normally geared towards the automotive industry, but also in the aerospace industry. And what it does is it says, I'm going to have a more sophisticated material model to represent the so-called trim material. And the trim material are the carpets, the padding that's underneath the carpets, the foam material that's on the dashboards, even the seats as well. And when we do that, what we're doing is we're combining our technology that's in MSC Nastran, body and white, and now we're going to include this trim component material and our acoustic cavity to get the frequency response in our enclosed cavity. The results of this, it's like any sort of damping material, but we have a more sophisticated damping model, is we're going to reduce the peaks from the case of no damping to damping, and we're going to, in general, we're going to bring the peaks to lower frequencies. So here what we're doing is we're comparing this with Actran. Actran is our sister product from FFT, so we're combining these two pieces of technology in a single, easy-to-use solution mechanism. Well, there is a slight challenge for people, and that is you have to be able to model this foam material. You have to be able to model the carpet material. But that's not that difficult, because if you would have your body in white, or if you were an aerospace structure, if you had the floor of your fuselage, you would effectively expand your plate elements or your shell elements, generating a set of hexahedral elements or pentahedral elements. They could be lower order elements or higher order elements. So to build one of these meshes is not particularly difficult to do. And then you would use the P-solid option to indicate whether or not it's a conventional element, meaning it's your metal element, whether or not it's a poroelastic material, or whether or not it's the fluid element in the particular model. So to simplify the computation, you can simulate just looking at the trim material and save that into a super element so that you can use it in subsequent analysis. So if you had a structure and you weren't quite convinced that what you needed in terms of the shape of the structure, but you felt that the floor of the structure was the same, you could do this just once and then reapply it in subsequent analysis as well. Moving forward. The second part of this is the material properties. So this is not like an isotropic material. It basically uses Biot theory to figure out what to do. There's a new material option called MAT-PE1, and the best way of explaining this is that in this material we have our traditional structural behavior, we have behavior that represents the fluid, which we enter through MAT-10, just like in an interior acoustic cavity, and then we have an additional set of properties that are going to be used to form this special frequency-dependent damping analysis. The other issue is in terms of the interface, the coupling. You can either have this material have an impervious type interface boundary condition, or you can say that it is glued to the structure, or that even the carpet can effectively slide along the structure. So there are other boundary conditions. And normally when we do an acoustic analysis, we don't need to have a coincident mesh between the cavity and the structure. Same thing here, we don't need to have a coincident mesh between the cavity and the trim component, or between the trim component and the structure. So here we'll use our cavity to come up with the interface, and here potentially we would utilize contact to come up with the interface. If you have an existing automotive structure and you already have the structure and you've built your fluid cavity, you don't have to restart the world. What you can do is you can say, I have a trim material and it overlaps the existing fluid cavity and the structural cavity, and we will basically map that geometric mesh that represents the trim material to where it belongs. Or if you're starting out from scratch, you can basically model the structure, model the cavity, and then model the trim material so that you have a nicely aligned finite element mesh. So we think this is a very powerful capability. We know that if people have the sensation that they have a quieter behavior in an automobile or a airplane, they're more satisfied users, and of course that generally means greater revenue to those who are producing those structures. Performance. Performance is always important. In MSC Nastran 2013, we have a variety of performance enhancements. The first one I want to talk about is in SOL 400. SOL 400 is, of course, the nonlinear solution sequence for implicit analysis in MSC Nastran. When we do a nonlinear analysis, as opposed to traditional linear analysis, usually the solution time is dominated by forming the stiffness matrices. So this is an effort to reduce the time associated with these stiffness matrices in reasonably large models. So here's an example of really between going from 2012.2 release to the 2013 release. We see somewhere in model sizes have changed. It's very dependent upon model sizes, but between 10 and 20% improvements in performance. If you have models with complicated material laws, or if you have models that are, let's say, with composites, with a composite failure in many, many layers, then what you'll see is a greater improvement in the computational performance. If you look at just the key portion, which is the elements assembly portion, and you can look at speed ups or what we call efficiency compared to the number of processors, we see that anywhere from about 80% efficiency to 100% efficiency, even more than 100% efficiency. So what this really indicates is by doing this parallelization, we got better utilization of the memory architecture, we got better utilization of the I/O architecture to improve the performance. When we're doing parallel processing with Nastran, with DMP, there's an option called domain solver. Probably many of you are familiar with that option. But now what you can do is you can say whether or not you want to do parallel processing on forming the set of equations, or whether or not you want to do parallel processing on the stiffness matrix, or you want to do parallel processing on both of them. Another improvement that was made, especially focusing on ACMS for large modal analysis, was improving the ACMS processing for DMP-type architectures, and particularly the combination of DMP and SMP, or DMP when we went to DMP equals 4. So this was an automotive model from one of our users, about 30 million degrees of freedom, 3,500 modes, around 324 scene frequencies. And what we can see is really for the less parallelism, there's not substantial improvements in performance, but when we go to DMP equals 4, SMP equals 4, between 2012.2 and 2013, we get substantial amount of improvement. And it's important to recognize that really between this serial run and this run here, it's about a factor of 5. It's the difference between a job running in about 30 minutes and a job running in about 2.5 hours. So we can see that a lot of improvement has been made, and we now have users who are really running models in the range of 90 to 100 million degrees of freedom, extracting as much as 10,000 modes in the structure. Another improvement has had to do with the memory utilization. We started this in 2012.2, and it was for SOL 101 and SOL 400. Now it's available on all the solution sequences. It's known as memory equals max. It is now the default in MSC Nastran 2013. So if you do your installation and you don't change the question that's given to you, it will now use by default the maximum memory. It doesn't use really the maximum memory. We still try to be friendly to the other people in the room. But we take a large chunk of memory, we divide it into the user space and the buffer pool space, and we will get improved performance. And depending on the particular job, again, you can see as much as a factor of 2 between, let's say, having an older technology where you said MEM equals, 400 megabytes and saying MEM equals max, because more things will run in memory, there'll be less I/O performed, and that will get to improved wall time. Another area of performance gains has to do with GPU computing. This is working in conjunction with our partners at NVIDIA. GPU computing was available in MSC Nastran 2012.2 for SOL 101 for linear systems, real symmetric systems. Now it's been expanded to non-symmetric systems and to complex systems, so we can use it also for SOL 103 and SOL 108 very effectively. And you can change some of the system cells, and you can even get improved performance. The computational improvements are key to having very compute-intensive kernels. So if you have systems that are very dense, then we have basically a case of larger fronts, and we say improved scalability. This is a SOL 101 run, and the bigger the front, the greater the scalability that occurs. So compared to a serial run, it's anywhere between 5 and 8 times faster. Compared to a multi-core type architecture using SMP equals 4, then we'll still get typically a factor of 2 to 3 times faster. So it's very cost effective. Here is a case of SOL 108, which wasn't achievable before, and we see a combination between a single serial run to 1 core and 1 GPU, all the way down to the case of DMP equals 4, SMP equals 4, so 16 cores altogether, and 4 GPUs, 1 GPU running off each socket, and we can see that effectively we have something that is 23.5 times faster. So we're talking about a job that was before something that took 16 hours, and now it basically takes, you know, a third of 1 hour. So substantial improvements in terms of the wall time for large models, complex models in the system. There are additional ways to improve the performance. MSC Nastran, of course, is very famous for giving accurate results. And one of the ways that it ensures accuracy is by the pivoting techniques when it solves systems of equations. So that's very good when we have buckling problems which are ill-conditioned, when we have Lagrange multipliers in our system, when we have thin shells and beams. But for other problems which are well-conditioned, one can now have some additional control on the pivoting algorithm, and if one utilizes that and recognizes that everything is a balance between performance and accuracy, but you can get another 10 to 20% type of improvement on this model that was on the order of 15 million degrees of freedom. So, of course, whenever you have such a model, you always want to get the best of the best, and every 10 to 20% may count for you. Finally, in terms of performance, I want to talk quickly about SOL 700. SOL 700 is, of course, our explicit solution. The focus really has been on the Eulerian aspect, the fluid aspect of doing fluid-solid interaction. The Lagrangian aspect of SOL 700 has parallelized very well for a long time. So we have done some more work in terms of tuning the MPI or the I/O operations that go between different chunks of the fluid or different domains of the fluid. And you can basically control the number of processors on a SOL 700 job using DMP 700. And this is kind of a nice way of looking at things. When we were in version 2010 and we had 32 cores, we could get maximum speed up of about 16 or 17. And nowadays on a 32-core system, we can get speed ups of somewhere between 26 and 28 in terms of maximum type numbers. Again, everything is quite problem dependent as to how much the performance gains are going to be. There have been a couple of other improvements on Dytran. We'll get to some of them later, but one of the things is in the area, SOL 700 improvements. One of the areas is in migration tools between Dytran and SOL 700. MSC Nastran SOL 700 is the go-forward solution for explicit dynamics. We want to reduce the pain of migrating to this solution sequence, but we think the benefits are clearly in terms of robustness and performance, and so we've added some additional tools for that. Let me move on to something called FRF, FBA, TPA, or frequency response functions, frequency-based assembly, and transfer path analysis. We've introduced a new option that allows you to calculate the intercomponent forces. It's actually easier to just show it. If you would think about this assembly of the nose cone and the two wings, the fuselage, and the tail section, so this is an assembly that we're going to do in the frequency domain as opposed to the displacement domain. And what we would be interested in is calculating out what are the forces, the total forces between these different parts of the assembly. So we have some new options that allow you to do that. And it stands for intercomponent force generation, intercomponent force use, and the combination of those two things. So what you'll get out is you'll get out the information of what is the force transmitted as a function of the frequency. There have been some enhancements to SPCD. SPCD was not available for SOL 400 in the previous release. It is now available in SOL 400 as well for performing dynamic analysis where you want to give a constraint in terms of the relative displacement between increments or between load cases. Other dynamic enhancements is an ease of use. When you had a large number of R load 1s, R load 2s, T load 1s, T load 2s, you gave each one of them a different load set ID, and then the deload option was very long because you had to mention each one of these load set IDs. So now what you can do is you can give the same load set ID to all your load options, and then the deload option is easier. Also, if you're using different scale factors on these loads, you can apply the same scale factor for all the loads which have the same load set ID. So that makes life easier as well. Something that's related to dynamics, or certainly was first implemented for dynamics, is something called monitor points. Monitor points is something I think is underutilized with MSC Nastran, but it's a very powerful tool because it allows you to look at a single piece of output and get a lot of physics out of that single piece of output. It was available for a variety of solution sequences. What we've done in 2013 is we've added it to another solution sequence. In subsequent releases, we're going to do some more enhancements for monitor points, controlling monitor points with coordinate systems, and adding additional solution sequences. So both MON.2 and MON.3, I think even MON.3 is even a more interesting way to obtain information and to be easily to interpret that information. Another area of dynamics and enhancements has to do with improving the interoperability between MSC Nastran and the Adams product. The mechanism of interoperability are these MNF files, or modal neutral files, but now we can use this in conjunction with SOL 400 so that we can preload the structure, then calculate the eigenmodes of the system based upon that preloaded structure, then obtain the Craig-Bampton modes, then create the modal neutral file, and then migrate that over to Adams. So in structures that are, let's say, are very flexible, let's say a long wing, where you had a fuel load in the wing, then that preload has an influence over the deformation of the wing, and of course it obviously has an influence over the modal frequency, the modal content of the wing structure. Another example, which is being shown here, is basically a blade. This is a helicopter blade, and if you would think about a blade as we spin it, then effectively the blades go into tension, the stress increases, the so-called initial stress increases, therefore the frequencies, the modal frequencies of the system increase as well. So we can take a look at if we would have done this based upon a unloaded structure or the conventional approach in previous releases, or if we had done this centrifugal loads in a Sol 400 manner, calculated the modes, and then created the modal neutral file, then of course what happens is the structure changes and the Adams dynamic analysis changes as well. In this particular problem, the rotational velocity wasn't particularly high, but you do see that there is a different behavior in these root sections because of the pre-stiffening effect. So I'm going to use this opportunity to thank all the people who were beta testers. Really, all the features that I've shown so far were part of the beta program. We encourage people to be participants of the beta program, and this was a particular aerospace customer, and they basically were, very happy with this procedure to calculate the modes, because before they did this writing out DMIGs and then reading back the DMIGs and calculating their modes, and this was a much easier approach. The next topic I want to talk about is UDS, or User-Defined Services. User-Defined Services are our mechanism to allow you to customize the product through user subroutines. There have been several advances in the use of these user subroutines in this release, and there will be continued improvements in the subsequent release as well. So they break up into really three groups. One is we've introduced a way to have state variables into the system and allow those state variables to be used in the user subroutines. Get to that a little bit later. We've introduced two new user subroutines, one called UMAT, which is really very similar to the hypoelastic routine, U-hypel-up. And we introduced a new user subroutine for cohesive material modeling for delamination analysis and composites. And finally, what we've introduced is a capability to, within your user subroutines, call utilities to get additional results in those user subroutines. So why did we do this multiple state variable and expand the capability? It has a lot to do with partnering with a variety of suppliers of material models for composites, including our partners E-Extreme and their product Digimat. So this allows, will allow Digimat to supply a component that fits into Nastran that will allow advanced composite modeling, advanced failure analysis of composite plies. So here was a little example. It's a uniaxial test specimen, and we load it up, and we noticed that the solution isn't exactly symmetric, and that had to do with the composite ply layout in this particular component. This is quickly, again, these two user subroutines that were used and the MSC Nastran options that are necessary to trigger the use of these user subroutines. Also an option called notify that allows, can kind of give you a signal as to when things happen and allows you to introduce data in a variety of locations in the program. And finally, these utility routines. The utility routines are quite useful. So within a user subroutine, you could do a reference to get global parameters, and it will tell you what's the increment number or what's the time during that particular step. Similarly, there are a series of user routines, or there's a single function, a get element param, and it will return back a large amount of information. So let's say you wanted to have the strain energy density at a particular layer point of a particular integration point of a particular element, you could do it in this way. And in an analogous manner, there's a similar thing for nodal values, such as to determine the acceleration at a particular grid point in the analysis. Moving on to optimization, well, we talked a little bit about optimization in conjunction with fatigue. We've also added some optimization capabilities in conjunction with ERP, equivalent radiated power. This is generally used in the automotive industry to get a quick evaluation of the acoustic content that's transmitted. And these values can now be used as an objective function, so we could say minimize the ERP, the radiated power up on a particular panel, or we could say design or change the thickness of my door such that it satisfies the constraint on the amount of radiated power. This is only available in the 2013 release for sizing optimization. It's not available for topology optimization. Input cards, defining the panels associated with ERP, there's really no change. And on the DRESP1 option, there's a new response type called ERP. Similarly, for fatigue, there would be a new response type called FAT. Other enhancements for SOL 700, we have a new capability for mapping the data from a 1D analysis or an axisymmetric analysis into a 3D analysis, typically used in blast loading, where initially your blast increases in a spherical manner, but it's not too exciting until you hit a structure. So you could do really a one-dimensional analysis to begin with, and then say, stop my analysis, restart my analysis, and basically say, okay, utilize the previous information and this option to map the data. So here's an example of mapping what I call a spherically symmetric 1D type of analysis into a 3D analysis. There are a couple of options. It's di-param, axial sim, or spherical sim. This would be done on the first analysis, and it would create a solution file, and then on the subsequent analysis, you would indicate where that previous file was, and you would basically tell it to do the mapping from a axisymmetric type formulation to full 3D, or a spherical formulation to full 3D. Another capability that was added had to do with blast applications, the ability to deal with multiple detonations. So you would have 2 or more blasts. They would be each controlled by an equation of state-type formulation, but you could basically say that I wanted this one to occur now and the next one to occur in 3 minutes, and it would do the input for you in an easy way. There is another blast model as well, predominantly for military applications. It's really implementing the expression that was done by Randers, Pearson, and Bannister. It's well known in the so-called ConWeb program. It is now available in MSC Nastran Sol 700 as well, and it allows you, you know, more information, you need more material data to do it, but you'll get a more better correlation with physical problems. So finally, I wanted to say that some of these new capabilities require additional licenses, and that has to do with our relationship with some of our partners. So the Poroelastic capability requires a new license key, and the MSC, the MSC Nastran embedded fatigue also requires a new license key, and the enhancements to GPU, if you already have a GPU license, then you do not have any additional license keys that you need. So if you had one from the 2012.2 release for Sol 101, that will now work for Sol 103 and Sol 108. Otherwise, if you want to use this technology, you will need to get a new license key. So if you're interested in these, and as I say, we will have another seminar on Nastran embedded fatigue. If you're interested in these, please contact your account manager, and we will be happy to help you out in that regard. So with that, I'd like to thank you very much for your attention.